Hello, welcome back. In the last video, we looked at the problem of statistical testing, and specifically statistical testing for a hypothesis about the population average when we assume a normal distribution for the responses. One of the things, the issues that we kind of glossed over, and we're going to do more carefully this time, is that in addition to the population average, the normal distribution has a variance parameter, sigma squared. So in the last lecture, we just assumed that we knew sigma squared to make things simpler, but in real life, we will not know it, and we need to do something about it. So that's what we're going to do in this lecture, and then in addition, we're going to move on to simple linear regression. So to review, we want to know about a population average from a sample of data that we're going to label little y1 to little yn. And we like this particular model for the data, that the individual yi's are independent, that's the IND, with normal distribution with mean or expected value b0 and variance sigma squared. Now, one notational change from before is that I'm going to be using b sub 0 here. It will become clear why I'm making this change when we go to simple linear regression. No need for a cliffhanger. We're going to have another parameter b1 in that model. So that's to distinguish this parameter from b1. This symbol here means is equivalent to. So an equivalent way of writing down this model is to say that yi equals b0 plus epsilon I, where epsilon i's are independent normal, mean 0, with the same variance sigma squared. So what I mean by that is if you take this formula, you can deduce that y has a normal distribution because it's a non-random number plus a normal distribution. So it's just a shift of a normal distribution. And once you know that something has a normal distribution, all you have to do is figure out what its expected value and its variance are. And in this case, the expected value of this normal variable is just b0 because it's a mean 0 normal variable epsilon I shifted by that amount. And shifting it doesn't change the variance, so the variance remains as sigma squared. Okay, so in this case, we want to know about the population average, so b0 is the parameter that we're interested in. So we'll call that the population mean or population expected value. And sigma squared is this variance. So how do we estimate b0? So the first thing I want to introduce you to is the concept of this residual sum of squares criterion. So we're going to look at that. So the way this works is we specify a candidate for b0. I'm calling that b0 star. So when you see this, just think of this is something that you specify. I'm going to say b0 star equals 8, something you pull out of thin air. Then for that candidate, you can define what's called a residual, which is just the observation yi minus that candidate. And then once you have this, you can compute what's called the residual sum of squared, or the sum of squared residuals for this particular candidate, which is the sum I equals 1 to n, yi minus b0 star, which is the residual, and then you square it. That's why it's called the residual sum of squared, or the sum of squared residuals. So what does that look like in a picture? Here's a plot here. On the horizontal axis, we just have I, so I'm just, 1, 2, 3, 4, 5. So there's no covariate in this case. I'm just using this axis to spread out the observations. And then the vertical axis is the actual observation, the yi's. So for this candidate b0 star, I can draw a line across. And then the deviation between each observation and this line, so in this case here to here, is the residual. And then you square that number and then add up all those residuals. So what we'd like to do is we want this line to go through like the middle of the data. And so what we're going to do is we're going to try a bunch of different candidates, b0 star, which is like sliding this purple line along this vertical axis. And what we're going to settle on is the value of B0 star that minimizes this criterion. So if all of the squared residuals are small, or the sum of the squared residuals are small, that's good. That means the B0 star is close to the observations yi. And then we define our estimate B0 hat to be the value of B0 star, the particular candidate that minimizes this residual sum of squares. So what that means mathematically is if we plug B0 hat into this function, residual sum of squares, it's going to be smaller than the residual sum of squares with any other particular candidate plugged in. So this notation might be a little bit confusing at first because we're introducing another symbol here, B0 star. How I want you to think about this is that this is just the input to a function. So if you think about, for example, the function y equals x squared, x squared is like the input to that function. So this is just something that you can give and you can calculate a residual sum of squares for, and you want to pick the value of B0 star that minimizes this residual sum of squares. I just want to have a different symbol from B0, which we're going to think of as the true value of that parameter. Okay, so in summary, this B0 hat is the solution to a minimization problem. It's the value of the parameter that minimizes the residual sum of squares. Okay, so this might seem like we're overcomplicating things a little bit. We want to estimate a population average. Why don't we just take the average of the data and use that? The reason for introducing this concept is that when we go to more complicated models, like the multiple linear model, there's not going to be an intuitive, easy to express formula for what the estimate should be. And in those cases, we're going to want to just use the residual sum of squares criterion to define what our estimates are. Luckily, though, in this case, where there's just one parameter, the minimizer of the residual sum of squares is simply the sample average. So all you have to do is to minimize the residual sum of squares is take the average of the data, and that is the minimizer of the residual sum of squares. This is convenient because it makes it easy for us to figure out what the sampling distribution of the estimator is. So remember our notation that little b0 hat is our estimate of the parameter b0. And that means it's just a number. It's something you can calculate on a computer. And it's a function of the data. Now this big b0 hat is our estimator. And this thing is the same formula as the estimate, but wherever we see data, we're going to plug in our model for the data, which is the random variable yi. So I'm going to define this as this average of random variables as capital Y bar. Now, one thing to know is that since this is just a sort of a combination of normal random variables, what's called a linear combination, this thing will follow a normal distribution. And once you know that a random variable follows a normal distribution, the only two things you need to figure out about it are its expected value and its variance. And by the way, I'm going to use the terms mean and expected value interchangeably. This is a property of a probability distribution. It's like the center of the distribution. And where we're talking about sample averages of data, I'm going to try to use the term sample average. But sometimes I'll say mean for this quantity. So just try to keep those terms straight. Okay, so let's compute the expected value of this estimator. So expected value of capital B0 hat is the expected value of this thing. So I'm just plugging in our formula for B0 hat. Expected value is something called a linear operator. What that means is if you have constant times a random variable. So the sum of these yi's is a random variable. You can pull the constant out. So I'm pulling this 1 over n out. And then if you have the expected value of a sum, that's equal to the sum of the expected values. That is the linearity property. So we can, from this expression, we can go to this one. And then if we look at what's the expected value of each individual yi, well, we assumed that these were normal random variables with mean or expected value b0. So each of these things is equal to b0, so the formula becomes this. And now we're just adding up b0 n times. So this is just equal to n times b0, and then you divide by n and you get b0. Okay, this is nice, first of all, because the estimator is unbiased for the thing we're trying to estimate, which is b0. Okay, next thing is the variance, and this is slightly more complicated. The property of the variance is if you have the variance of a coefficient times a random variable, what you do is you pull the coefficient out, but you square it. So this 1 over n will come out of the variance, and it'll be 1 over n squared. Now, variance is not a linear operator, but it behaves the same way as expected value, where you can just pull it inside of the sum when, and only when, the observations are independent. So if these are not independent, you can't do this. So this equality only follows because the yi's are independent, or uncorrelated, to be more precise. This becomes the sum of the variances of yi. And these are all normal distribution, mean b0, variance sigma squared. So each one has variance sigma squared. So it's 1 over n squared times sum of sigma squared, which means we're adding up sigma squared n times. And this is n sigma squared divided by n squared, and you get sigma squared over n. Okay. So that means b0 hat is normal, mean b0, and I have a typo here that I'll fix in just a second. This should be sigma squared divided by n. Now what we can do is we can use this sampling distribution of our estimator, remember this is sigma squared over n, to come up with tests of hypotheses. So for example, if our hypothesis is that b0 equals 7, or any other number, we can come up with a decision rule which says reject the hypothesis if our estimate minus 7 is bigger than some cutoff. This is a reasonable thing to do. If the estimate is far away from the hypothesized mean, we should reject it. And then if we do the math in R, we figure out that C should be equal to 1.96 times the square root of the variance of the estimator, which is sigma over square root n, for alpha equals 0.05. Okay, typo fix here. Remember, this is sigma squared over n. All right, so there is one problem though. So our test is going to be based on the value of sigma, which we don't actually know. So we don't know sigma in reality. So there's some things we could try. One thing we could try is we could, instead of basing this cutoff on sigma, we could base it on an estimate for sigma. And let's think through how we would generate an estimate for sigma. Okay, so if we look at this quantity, which is just epsilon I is yi minus b0. So I'm just taking the model formula and I'm solving for epsilon I. This thing is normal, mean 0, variance sigma squared. And then if you square epsilon I, because it has mean 0, its expected value is equal to the variance sigma squared. So a reasonable thing to try is to just take the average of the data minus b0 squared and use that as the estimate for sigma squared. So I'm going to call this, I'm going to give you a few candidate estimates for sigma squared. So I'm calling this one sigma 1 squared. So this one, what you do is you take the data minus the true value of the population mean, square it, and take the average. Problem with this one is we don't know B0, so this is like a chicken and egg situation. We have to do this because we have to do something because we don't know sigma squared, but then this solution assumes that we know B0, which we don't know. So this is not going to work. Another thing we could do is, well, let's just plug in an estimate for B0. So just take yi minus B0 hat squared and take the average. So I'm calling this estimate sigma 2 squared. Now this is something we can actually calculate. This is data we have, and this is just the average of the data. And so this is something we can calculate. But there's going to be a problem with this one as well, and let me try to explain what the problem is. Since B0 hat minimizes the residual sum of squares, and if you look at this, this is just the residual sum of squares. So B0 hat is the value that you would plug in here that minimizes this thing. We know that sigma hat 2 squared, which is this estimate, which is equal to this, is less than or equal to 1 over n times the residual sum of squares with any other value plugged in here. And in particular, I'm going to plug in the true value of the population mean. So if I look at this quantity, and this is sigma 1 squared. So we know, if we look at these two estimates, we know that this one, sigma 2 squared, has to be smaller than this one. But we also know that this estimate is going to give an estimator that's unbiased. So we're in a situation where here's something we can calculate, but we know it's going to be smaller than the unbiased estimator, which means that it's going to be biased, and it's going to be biased downwards. So this estimate here is going to give us an estimator that's biased to be too small, and it's precisely because this B0 hat is the value that we plug in here that minimizes this quantity. So it's the fact that we're minimizing it, we're making it really smaller than it should be if we plugged in the true value of the parameter. So our solution here is to just make a little adjustment. Instead of dividing by n, we're going to divide by something a little bit smaller, which makes the whole thing a little bit bigger. We're going to divide by n minus 1. So our solution for estimate of sigma squared is to take this quantity, take the residual sum of squares with the minimizer plugged in, but instead of dividing by n, we're going to make a little adjustment and divide by n minus 1. And it turns out that this estimate gives an estimator that's unbiased. So this is the one we like, and so this is the one we're going to call sigma hat squared. I'm also going to give a different notation for this, so I'm calling this S hat squared. The reason for that will become clear in the next few slides. The reason is that I want to talk about this thing, the random variable version of this thing, and I don't want to capitalize sigma, but I can capitalize S. If I capitalize sigma, it looks too much like this. So this is just a notational thing. Okay, so where have we gone so far? We want to construct a test for this hypothesis. First thing we tried is to use this cutoff, but the problem is we don't know sigma. So one solution is to try plugging in an estimate for sigma. And we thought about how we would do that, and we settled on this one as a good estimate for sigma hat squared. By the way, to get the estimate for sigma, you just take the square root of this. Okay, now there's going to be one more problem that's a little bit more subtle. So let's go back to our testing problem. Here's our decision rule, and our proposed solution is use this sampling distribution. So this is not the real sampling distribution, but it's the sampling distribution of B0 hat where I'm plugging in this estimate for sigma squared. So it's the same formula, but instead of sigma squared here, I'm using the estimate for it, S hat squared. And then our cutoff is going to be C equals 1.96 S hat divided by square root of n if our significance level is 0.05. So the problem is this test, if you use this thing and figure out what the type 1 error is, probability of rejecting a true null hypothesis, it actually comes out to something different to 0.05. The reason for that is that for each sample, we're going to get a different s-hat. So this cutoff here actually depends on the data. And by doing that, we actually modify what the significance level is. So if we use this cutoff, it's actually not a test with significance 0.05. Now, what's the solution to this? It's kind of interesting. So there's a guy named William Seeley Gossett who worked for the Guinness Brewery in Dublin, but he was a mathematician. And he wrote a paper in 1908, writing under the pseudonym Student, and he suggested to use this statistic. So this is going to look very similar. So we're looking at just the estimate of B0 minus its hypothesized value divided by s-hat over square root n. So this has all the quantities we've been talking about. But the clever thing he did is incorporate the sampling distribution of s-hat into the statistic. So he's putting the s-hat as part of the statistic and then working out what is the sampling distribution of the estimator. By that I mean, this is our statistic. To get the random variable version, we take anything here that depends on the data and plug in the random variable that's used to model the data, which means that this thing, B0 hat, becomes random variable, and the estimate of the standard deviation is also a random variable. So this is all incorporated into the statistic. So here, big S hat is just the estimate of sigma hat, and this should be S hat squared, with random variables plugged in. So wherever I see little yi, I do big yi, and wherever I see little b0 hat, I do big b0 hat. So this is a sort of a different kind of random variable. And what Gossett worked out is he figured out what's the distribution of this random variable, and it turns out it's not a normal distribution, it's something different. And we now call this the distribution of this statistic Student's t-distribution, to remember the pseudonym that Gossett used in his paper. This distribution is slightly different from the normal, first of all, and it has an additional parameter called the degrees of freedom. In this case, that parameter is equal to n minus 1. So the cool thing about this is once we construct this estimator, we know what the distribution is. It's a t-distribution. And that distribution does not depend on things that we don't know, such as the variance of the distribution used to model the data. So this is kind of a interesting technical mathematical advance that he's incorporating the estimate of the standard deviation into the statistic. And it turns out that you get a different distribution than a normal. All right, so I fixed this typo here. This should be s hat squared. And then to get s hat, all you do is take the square root of all this. Let's put everything together now to see how we actually do the test in practice. So our model for the data, yi or independent normal, mean or expected value b0, variance sigma squared. Our hypothesis is about the population average or expected value. And I'm just plugging in a number here, b0 equals 7 for a specific hypothesis. The statistic we're going to use is this thing here, the t-statistic. So what this is you take the estimate of b0 hat minus its hypothesized value, and you divide or scale it by s hat over square root n. Now, the sampling distribution of that, the random variable version of the statistic, is what Gossett worked out. It's this random variable. And he worked out that it has a t-distribution with n minus 1 degrees of freedom. Now, the important conceptual advance here is that the sampling distribution of the statistic does not depend on anything that we don't know. So we know the only thing it depends on is the sample size, which we know. Whereas before, when we tried to construct a statistic, it depended on either sigma or an estimate of sigma. This just depends on n, and that's because we're scaling it by the appropriate factor. Now our decision rule is going to be to reject the null hypothesis if the absolute value of the statistic is bigger than some cutoff. And the reason why this makes sense is this thing is we're sort of measuring how far away the estimate is from the hypothesized value and then scaling it. So it makes sense to think to reject the null hypothesis if this thing is very far away from the hypothesized value after scaling. And then to calculate the p-value, you calculate the probability that the random variable is bigger than the actual observed variable. And to do that in R, you would do this. So let me explain each of these steps. So PT is the function for computing probabilities with the t distribution. The first argument is the value that you'd want to plug in, and then the second one is the degrees of freedom. That's the only parameter in the t distribution. So if we want to know what's the probability that absolute value of big T is bigger than absolute value of little t, this thing will give you the probability of a t distribution being less than this value. So for example, if we got little t equals 0.8, if you plugged in PT absolute value of t, df equals n minus 1, it's going to give you the area from minus infinity up to this value. Now we want to get the probability in the tails or the extremes. So we're going to do, to get this one out here, we're going to do 1 minus that. So the whole thing under the curve is 1. PT absolute value of t gives you the area from minus infinity up to here. So this red area is 1 minus that. And then we also have to add up the area that's less than minus 0.08. So this would be also considered more extreme than the one we observed. So we just multiply by 2. All right, and that's how it all fits together. And no nonsense here. This is actually how you would do it in practice under this normal assumption for the observations. All right, now let's take it up a notch, and we're going to talk about simple linear regression. So this is just a term that's used to define linear regression with a single covariate. So in this case, our data are going to be two different things. We have y1 to yn, which we call the responses. And then associated with each response, we have an additional piece of information, x1 to xn, that we call the covariate. And then our model for the data is the following. Capital YI is the random variable we're using. It's equal to B0 plus B1xi plus epsilon I. And our assumption about the epsilons is that they're independent normal variables, mean zero, variance, sigma squared. So anytime we write down a model, we're going to want to examine it, analyze it to determine what its properties are. So let's look at some properties of this model. So one of the properties you can look at is what is the expected value. So if you take the expected value of this thing, you take the expected value of this entire quantity, and the way this works is you pull out the non-random stuff, and then you do expected value of the epsilon, which is 0. So it's just this non-random stuff. And then the variance of this thing is sigma squared. The way this calculation works is you do the variance of this whole thing. Now shifts one way or another do not affect the variance, so you basically just ignore this part, and you do the variance of epsilon I, which is, by assumption, sigma squared. This model has several different things in it. One of them is the xi. Now the xi is different from the rest because the xi is something that you get to see. It's part of the data set. But the other stuff you don't get to see. So this parameter b0, we don't know what it is. Our goal is to try to estimate it. Same thing for b1. And then this random variable depends on an additional parameter, sigma squared. So this model has three sigma squared, three parameters that we don't know, b0, b1, and sigma squared. And how do we interpret these things? So one of the strategies we're going to use to generate interpretations for regression coefficients, in this case B0 and B1 are regression coefficients, is we're going to try plugging in specific values for the covariates and try to sort of isolate the coefficient and then come up with an interpretation for that. So if we look at this formula for expected value yi, it's b0 plus b1 xi. If we wanted to isolate b0, we can plug in xi equals 0, and then we would get expected value yi equals b0. So the interpretation of b0 is it's the expected value of the response when the covariate is equal to 0. And this thing we call the intercept. So it's what you expect to get when you plug in a 0 for the covariate. b1 we can interpret as the change in expected value yi per unit change in xi. This sort of quantity is often called a slope. I'll show you the picture in just a second. So in mathematical terms first, what do we mean by that? Say we take the first two observations and we take the difference of their expected values. So the expected value y2 is going to be b0 plus b1 x2. Expected value y1 is b0 plus b1 x1, but we're subtracting it. So this is minus b0 minus b1 x1. And then the b0's cancel, and then you get a b1 in both of these, so you can factor it out. So you get b1 times x2 minus x1. So the way we interpret b1 is this is the amount that expected value of yi changes per change in the covariate x. And in a picture, it looks like this. So on the horizontal axis here, we have xi. The vertical axis is expected value of yi. And then I'm just putting on this axis two values of x, x1, x2. If we were to plug in sort of x3 equals 0, we would get b0. That's this point here. And then if we were to look at the expected value of yi at xi equals 1 and xi equals 2, we get these two values. This is the change in x, and then the vertical is the corresponding change in y, and that's equal to b0 times the difference of the x's. So this is a simple linear model. Obviously, it's called linear because you can connect all the expected values along a single line. So those are some properties of the model. The next thing we want to do is to try to figure out how to use the data to generate estimates of the model parameters. And then now here's a case where this residual sum of squares criterion is going to come in handy, because if you just start to think about how you would generate an estimate for these parameters, it's not obvious how you would do it. So we're just going to follow our instincts and say, let's pick the parameters that minimize the residual sum of squares criterion. Okay, so here it is. Now the residual sum of squares criterion is going to depend on two numbers, our candidate for the intercept and our candidate for the slope. And this is the criterion. So we're just going to take yi. This should have a dot over this. This is yi minus b0 star minus b1 star xi. So this is just yi minus its expected value with candidates plugged in for the parameters. And then the idea here is we're just going to try a bunch of values for b0 star and b1 star, which means like trying a bunch of different values, trying a bunch of different lines that go through the data, and picking the one that minimizes this sum of squares criterion. So again, even though b0 hat and b1 hat are defined as solutions to this minimization problem, they again have formulas that we can write down. And these ones are somewhat simpler, but a little bit more complicated than the previous case where it was just the sample average. And here's the formula. Typically, we'll write down the formula for b1 hat and then write b0 hat in terms of that formula, in terms of that estimate for b1 hat. So here's the formula for b1 hat. We take this quantity, so xi minus x bar, which is the average of the x's, yi minus y bar, which is the average of the y's, multiply them together, and then sum it up over I. And then we take sort of the sum of squares of the x's and add them up. The thing on the top we're going to refer to as SXY. So this is like the sum of the deviations of x multiplied by the deviations of y. And then this thing we're going to call SXX. So this is the sum of the deviations of x multiplied by themselves because it's squared. I'm not writing it down here, but you could also have SYY, which would be the sum of the deviations of the y's squared. So that's the formula. This is something that just depends on data. Xi is data, x bar is the average of the data, yi is data, y bar is the average of the data. So this is something we can calculate after we get the data. And then b0 hat is just this formula. We take y bar and subtract b1 hat times x bar. So this again is something that we can calculate. No tricks here, we can just do it. Our estimate of the variance, we're going to use these residual sum of squares. It's going to be this is a typo. This should just say 1 over n minus 2 times the residual sum of squares, not the sum of them, which it would be equal to this thing here. So our estimate of the variance is we take the residual sum of squares, and instead of dividing by n minus 1, we divide by n minus 2. And we'll talk a little bit later in the lecture about why it's n minus 2 instead of n minus 1 in this case. Next thing to do is once we have a formula for our estimates, we can look at the random variable version and work out their sampling distribution. We're not going to go through the math of how you get these answers, so I'm just going to give you what the sampling distribution are. B1 hat has a normal distribution with expected value B1 and variance sigma squared over SXX. This is great because it's unbiased for the thing it's trying to estimate, which is the slope, B1. B0 hat is also normal. It's also unbiased for the thing it's trying to estimate. And here's the formula for its variance. It's sigma squared times 1 over n plus the square of x bar divided by SXX. Now, one interesting feature of these sampling distributions is that B1 hat is not independent of B0 hat. So these have dependence between them, and we measure that dependence by their covariance, and the covariance is this quantity here. So you can think of covariance, it's like an unscaled correlation. So correlation is scaled to be between 0 and 1, minus 1 and 1, and the covariance is sort of, it's a number that could be negative or positive that measures the strength of dependence between two random variables. So what this means is that B1 hat is not independent of B0 hat. So this is something to keep in mind. Cleaning up a bit here, I fixed this typo. Sigma hat squared is the residual sum of squares divided by n minus 2, which is equal to this formula here. All right, now I want to talk about degrees of freedom, and this gets to why we're going to divide by n minus 2 instead of n minus 1 in simple linear regression. So the way I like to think about degrees of freedom is that there are these two complementary types of degrees of freedom. And the one that we call degrees of freedom is the second type, but I want to talk about the first type first because it's a little bit easier to understand. And the first type I'm calling the model degrees of freedom. So most of the models that we'll study this semester look like this. It's going to be yi, or independent normal, with some mean, mu I, which might be different for each I, and some variance, sigma squared. So the very first model we looked at, the mu I was equal to the same value for each I, namely B0. The second model we looked at, here, the example is down here, was B0 plus B1 xi. So mu I is the mean or the expectation, sigma squared is the variance. The way I'm defining model degrees of freedom, it's the minimal number of parameters required to specify the mean part of the model, namely the mu I. So the first model, mu I was B0. We only need one number here to specify what the mean is. So this model has one model degrees of freedom. The second model we looked at, simple linear model, mu I is b0 plus b1 xi. So this has an intercept and a slope, which could be two different numbers. So this model has two model degrees of freedom because you have to specify the intercept and the slope to tell what the expected value is. So in many cases, this model degrees of freedom is going to be equal to the number of parameters describing the mean, but not always. And this is really important. We're going to come back to this when we talk about factor models. So let me give you kind of a simple example to show you why this makes sense. So suppose we wrote down this model for the mean, b0 plus b1 xi plus b2 xi. Now this specification is redundant because we have two terms that are linear functions of the covariate xi. And so we could take this model formula and just rewrite it like this, b0 plus b1 plus b2 times xi. And now you see that suppose the true slope was 7. So we could have 0 and 7, or 7 and 0, or 3 and 4, or 4 and 3. And it all specifies the same exact model. So this model, even though we're writing it down with 3 parameters, 2 of them are redundant and can become collapsed into a single parameter. And therefore, this mean model has only 2 model degrees of freedom because these 2 parameters are redundant. So we're going to look at this in a little bit more depth when we talk about factor models. I don't want to give you incorrect information and say that the model degrees of freedom is equal to the number of parameters. It usually is, but there are some cases where the models are specified in a way that makes some of the parameters redundant. So think of this as the sort of the minimal number of parameters you need to define the expected value. And for our purposes at this point so far, it's just you count up the number of mean parameters. Now the complementary notion of degrees of freedom, I'm calling the residual degrees of freedom. And like I said, this one is often if someone says degrees of freedom, what they're talking about is this one, the residual degrees of freedom. And this is not complicated at all after you understand what the model degrees of freedom are. It's just n minus that. So n minus the model degrees of freedom. The reason it's called residual degrees of freedom is we think of this as it's the degrees of freedom left over in the data that we use to estimate the variance parameter. So what we do to estimate the variance parameters, we do the residual sum of squares. Take the residuals and square them, add them up. And we divide by the residual degrees of freedom. So this is going to be our strategy for estimating the variance. Turns out if you do this, you get estimators of the variance parameter that are unbiased. Okay, so for the 2 models we looked at so far, the first one is this one. Model degrees of freedom is 1. Therefore, residual degrees of freedom is n minus 1. That's why we divide by n minus 1. For this one, model degrees of freedom is 2. Therefore, we divide by n minus 2. And when we talk about the degrees of freedom in the t distribution, we're talking about the residual degrees of freedom. All right, now let's see how to do testing for the simple linear model. And we're going to do t-tests here. And I'm going to have to introduce a little bit of new notation for you. So we saw before, when we worked at the sampling distribution of b1 hat. By the way, we're going to go through and do everything for the slope parameter b1. And then we're not going to show you b0 hat, but everything is exactly the same. You just plug in zeros for ones, and you have to plug in the right variance formula here. Okay, so the variance of b1 hat, which comes from the sampling distribution, is sigma squared over sxx. And what I'm going to call SE for standard error is simply the square root of that thing. Now, we somewhere along the way, someone wanted to distinguish between standard deviation of observations versus the standard deviation of the sampling distribution of the estimators. And so they call that thing the standard error. I think it's a little bit unnecessarily confusing. So all we mean by standard error is it's just the standard deviation that appears in the distribution for the estimator. So if you see standard error, just think standard deviation of some distribution. It happens to be the distribution of the estimator of our parameter, which is simply the square root of the variance. Okay, moving on to the middle column. We're not going to know sigma squared in practice, so we're going to have to plug in an estimate. And I want to distinguish between the population variance and our estimate of the variance. So I'm going to call this little var hat. And all that is I take this formula, sigma squared over sxx, and I'm going to plug in our estimate, s hat squared. So this is a non-random quantity that depends on the data, and it's intended to estimate sigma squared. So little var hat b1 hat is s hat squared over sxx. This is our estimate of the variance of b1 hat. And then if you take the square root of that, I'm just calling that little se hat. Now the third column is just the random variable version of the middle column. So wherever I saw little s hat, I'm going to do big S hat, which is the random variable version. And the notation I'm going to use to follow our convention that capital letters mean random variables is I'm going to capitalize VAR. So big VAR hat B1 hat is our estimator of the variance of B1 hat. And then we can also talk about the square root of that quantity, which is also a random variable. I'm going to call capital SE hat B1 hat. Now to keep things straight, let me just remind you what the conventions are. Lowercase means non-random. So this little VAR is a non-random quantity. Little VAR hat is non-random, but big VAR hat is a random variable. Hat means we're doing an estimate or an estimator, depending on whether it's non-random or random. And then standard error just means square root of variance. So if you take the square root of a variance, you get a standard error. Okay, now we have the notation to define our t-statistic. The t-statistic is our estimate of the slope minus its hypothesized value divided by the sample standard error. So this thing are things that just depend on the data and our model for the data. So this is just a number that we can plug into a computer. Now the random variable version of that statistic, wherever we see something that depends on data, we plug in the random variable version. So little b1 hat becomes big b1 hat. And little se hat becomes big se hat. This is a random variable, and it has a t-distribution with n minus 2 degrees of freedom. So remember, when we talk about the degrees of freedom in the t-statistic, it is the degrees of freedom, the residual degrees of freedom. So it's the degrees of freedom associated with the estimate of sigma squared. And then to get a p-value, we could use the pt function in R, and it works the exact same way as before. You do absolute value of our observed statistic to get the probability to the left, and then you do 1 minus pt to get the probability to the right, and then you have to double it for the complementary region on the opposite side. Like I said, this will all work exactly the same way for little b0. We're going to have the same sort of notation, except the only thing that's different is that the formula for the variance is different. All right, now the last thing I want to talk about in this lecture are measures for the strength of dependence between x and y. So if we look at these two scatter plots here, x on the horizontal, y on the vertical, we would probably say that the dependence between x and I is pretty weak in this case. It looks like the expected value of y increases a little bit as we increase x, but there's a lot of deviation around that. So this is, we might say this is weak dependence between x and y. Whereas here, this is a pretty strong dependence between x and y. Now, we know how to calculate p-values from the previous page, but one thing to remember is that the p-value is a measure of the strength of evidence against a hypothesis. So if our hypothesis is that there's no relationship, the p-value just measures how strong is our evidence against this hypothesis. The p-value is not a measure of the strength of the relationship. Some people will say that, p-value is really more a measure of how much data you have. I'd say that it's a measure of how much data you have and whether or not the hypothesis is true or not. Okay. Now, to measure the strength of dependence between x and y, we're going to have to look at a couple of different metrics. And here are some of the common ones. So one thing you can look at is pretty simple. We're going to get an estimate of sigma squared. And so we can look at this thing and try to interpret whether this is big or small. So in this case, we might say sigma squared is pretty big, whereas in this case, it's pretty small. But that doesn't get us quite all the way there because we really need to measure how big the deviations are relative to how much the expected values change as a function of x. And one way of doing that is with this quantity here. So this is the ratio RSS over SYY. Remember, SYY is just the sum of the deviations between, sum of the squared deviations between yi and y bar. So this is the ratio of variation in the residuals to the variation in the response. So if we look at this, variation in the response is just going to be the deviations around this horizontal line here. And then the variation in the residuals are going to be the deviations, some of the squared deviations around the best fit regression line, which would look something like this. And in this case, those two deviations are going to be pretty close to each other. Of course, the RSS will be a little bit smaller, but they'll be pretty close. So that would tell us that the deviation doesn't decrease very much if you use the best fit line versus just a horizontal line. Whereas in this case, it's going to decrease a lot. So this thing will have small deviations around the best fit line, but bigger deviations around the best horizontal fit line. So this thing could be used to measure how strong the relationship is. And this thing is small when x explains y well. Now the reverse of that, if we just take 1 minus that, this is something called r squared. So this is a very common thing that people report. It's part of the summary when you print out a model fit in R. And the way people interpret this is it's the proportion of variation in the response that's explained by x. And this thing will be large, namely close to 1, when x explains y well. Another thing you can do is to look at the width of a prediction interval. And this is very closely related to what this is. So here's the problem. So suppose we get a new subject with a new covariate value xn plus 1, but we haven't observed the response yet, yn plus 1, and we want to predict it. Our prediction is going to be y, I'm going to call this y hat n plus 1. And this just depends on the new covariate value and our current estimates of the intercept and the slope. Now the random variable version of this is capital Y n hat n plus 1, where we're plugging in random variable versions here. And the measure of how well x predicts y is going to be the variance of this. So this is the variance of yn plus 1. Remember, the formula for yn plus 1 is the same as this, but it involves the true little b0, the true little b1, and then you add the residual. So this thing is going to be b0 plus b1 x plus 1 plus epsilon n plus 1 minus y hat n plus 1. And our measure is the variance of this quantity. And I'm not going to go through the algebra. We could do that in an office hour. You get this quantity here. So this is our prediction variance for a new observation. So it's going to depend on n. It goes down as n goes up. That's good. It's also going to depend on how far away the new covariate is from the rest of the covariates. So the rest of the covariates, their center is x bar. And so this prediction variance will go up if we're observing something that's much different from what we've already observed. And then you add a 1. This comes from the fact that we have this epsilon thing. So there's a part of this prediction that more data will never give you more access to, which is this residual. They're always going to have the residual. Okay, so these are some measures of how we can measure the strength of dependence between y and x. So just to summarize, this will have a big sigma hat squared. This will have a small sigma hat squared. This will have a big RSS over SYY. This will have a smaller one. This will have a small r squared. This will have a big r squared. And this will have bigger prediction variances. And this will have smaller prediction variances.